Hello and welcome to the Miko Bits Show, and I'm your host, Miko Bits. Today we have Vincent from Mangrove Exchange. It's a very exciting exchange, so really interesting novel mechanism. Really excited to have our guest. So welcome to the Miko Bits Show.
Hey, hi, Miko. Very nice to be here.
Yeah, it's terrific. So, would love to understand sort of how you define the problem that you're solving
Well,
with Mangrove
yeah.
Exchange.
So sometimes we call it the supplier dilemma. So we think that the way liquidity providers provide liquidity today in traditional finance or in decentralized finance is kind of something we can improve on using modern technologies, blockchain. And I would say having a non-exclusive way to provide your liquidity, not having to pre-allocate your liquidity to position A, B, C, and just do it when it's needed. So kind of a reactive market liquidity provision is the what we're aiming at.
Yeah, that is hugely powerful. Just as a quick disclaimer or caveat for the audience, my fund, Gumi Crypto's Capital, is invested in Mangrove Exchange. One of the reasons we did so is that we do think that one of the crazy problems in DeFi is capital inefficiency, right? And I think this is traditionally measured by total value locked, right? So the idea that there's really huge piles of value that are locked and kind of really not needed and not doing anything, I think is really a pretty significant problem in DeFi. So I think you're really, solving capital efficiency, which I think is really important. So you're putting really more money to work, right? So I guess I would love to understand kind of how your mechanism works. So how is it that someone can be more efficient with their liquidity as supplied to something like a Mangrove Exchange?
Yeah, so the proposition is really simple in a way. It's just that as long as money doesn't have to change hands, liquidity really could be anywhere. So it's a bit foolish to lock it somewhere and not somewhere else. You should be able to put it wherever you want. The trick is that when you actually need to deliver, then there should be some kind of mechanism in place to move the liquidity from where it is to where it's needed. And so I think liquidity in general is some kind of absolute quality that the markets are trying to achieve, improve, or optimize. And using blockchain and the smart contract composability, we can, just by pure technology in a way, we can improve on how much liquidity is actually flowing through the pipes. And that's the idea. So that's what we're trying to do. Now, how we do it is also super simple. The idea is that we completely decouple the idea of declaring one's trading intentions. So you tell the market engine, I'm willing to sell that much of something at that price, as usual. But what's unusual is that you don't actually lock the one thing you're trying to sell inside the market. While you're declaring that you want to trade, you actually, instead of locking in what you want to trade, you attach a little piece of code, little or large actually, which is going to be in charge of delivering the said liquidity when your offer is matched by the market engine against any kind of consumer taker, as we call them. And so that's it. You just attach a piece of code to your offers. And just in case, for whatever reason, maybe intentional, maybe strategic even, or maybe unintentional, because your liquidity sources have changed somehow, if for whatever reason you can't deliver, or properly said, your code cannot deliver or decides not to, then you have to pay a little compensation to the taker. just what the taker needs to not having paid gas in excess of what it's actually getting for the gas it's paying. And so that tiny incentive is supposed to be enough to make you, force you to make credible offers and to not slight the taker if you're not actually delivering on your promise. So that's it. It's as usual. The actual data structure used is that of an order book, and an offer has all the classical data, how much you want to sell, what price. But it's got three additional attributes, technically. A provision to compensate the taker if you don't deliver, a request in gas, because you have to tell the market engine how much you're going to consume when trying to deliver. And the third thing is just a callback address to whatever contract on chain is going to be in charge of delivering. And we kept the design space as broad as possible. So now every use case actually has to find some way to make the most out of the ability to attach code to offers. And just to dispel one possible misunderstanding here,
Go ahead.
Everything is happening on chain. There's no delay. It's all done atomically. So the liquidity you can actually go and recruit has to be on chain and has to be something you can withdraw within the same transaction. If you have locked in your liquidity, well, it's locked in and you can't get at it when you have to deliver. So that's a limitation. And the other thing maybe which is a common source of misunderstanding is that you can attach the same code to multiple offers at once. So there's a contract which is your contract, totally yours to define. So the Mangrove project as a whole actually gives you little bricks to build and to help building this contract. But in principle, it's yours. The market engine completely ignores, it's completely agnostic to whatever your code is doing. So in a way, it's you have not only do you not lock up your liquidity, but you keep entire code-mediated control on what you're doing. And that piece of code that you yourself implement and deploy is going to be, in general, in charge of multiple offers on multiple markets. And that opens up a lot of possibilities, which we can discuss later on.
Yeah, I'm very interested to understand the strategy of a liquidity provider in this context, right? Because really the optimal strategy involves effectively making a promise, right? Because presumably supplying of liquidity earns the classical reward, right? But I would say that like the issue becomes that the provider doesn't want to be penalized for not being able to deliver. So I guess my question that I'm curious about is like, you know, it seems like the supplier of liquidity can potentially have their liquidity, you know, actively generating yields in some sense in two places at once, right? But I'm curious about kind of like how they juggle this obligation, right? Because in a sense, like they're going to need to have sufficient liquidity, you know, at any given time. So I guess that's a really interesting kind of mechanism. So I'd love to understand kind of how liquidity providers should think about optimizing their strategy.
Right. So that's exactly right. That's the key question. So you have, and to each his own, right? You have to write down your economic equation and balance between how many times you have to pay this kind of compensation because you pass on a trade and how much it's going to cost you in the end, and how many times you actually decide to deliver on your promise. And so it depends a lot on lots of things, on what you do, on what's the chain on which you're doing it. Right now we're talking about Polygon. Polygon is one of the cheapest chains in terms of gas price, and that's why we picked it as our first deployment base. And in that case, it's not so much how much it's going to cost you, because it's very little. It's more how much of computation size you're going to invest into one particular offer or in the contract that manages the offer. So to return to your question, I think the best is to give an example. So that's one thing you can do. Since you're attaching code, is you can actually declare an intention to trade while having zero capital. What's happening in the construction of a match by the market engine is that when the market engine calls your management code, it actually passes over the control of the cash, so to speak, that the taker is matching your offer with to your piece of code. So here you are. Your piece of code is woken up. Essentially, Mr. Market Engine says, hey, I have a match for you. So, please deliver. And here's the money that the taker has given to match your offer. So, do whatever you want with it. This is exactly in the matter of a flash loan. And as an aside, a trivial use case for Mangrove markets is to build flash loan markets if it's ever needed. So to return to the main thrust, your code is now equipped with the cash of the taker, and it has to deliver or not. And so one trivial way to do it, if you have no capital, is to connect to another source of liquidity, let's say, a nearby DEX, and to take the money of the taker and to buy whatever you promised to sell to that other source of liquidity, which is called liquidity retargeting or liquidity forwarding, which is kind of a practice also in traditional finance, but as you may expect, it plays out very differently because it's not done on chain, there's latency and so on and so forth. But so if you do this, then what's going to happen, and I actually simulated this a lot because it's a very interesting, very simple, basic use case. What's going to happen is that by the time you knock at the door of the other DEX with the money of the taker on hand to buy whatever you promised to sell, you're going to discover what the price of this DEX is currently, the marginal price or the execution price. Let's make things simple, and let's say there is a fixed price, volume-independent price. So now it may be that that price is a bit higher than the price at which you're selling, in which case you have a loss, or it may be a little below, and in which case you make a little profit here. Now, what you have to decide for yourself is whether you want to take the loss or how big the loss has to be. That is the delta of price, supposing you're selling a unit volume, between where you buy and when you're selling, that is on Mangrove. So how much does it have to be for you to renege on the trade and say, no, I'm not doing this, I pass. So that's a parameter of your behavior. And so this is a concrete example of what this kind of very broad question you're asking, which is how do you deal with, as a liquidity provider, with the correct soft spot, the good trade-off between passing too many times, too frequently, and leaking out some fines and being taxed for not delivering. And so in other words, how frequently do you fail to deliver? Actually, failures to deliver, FTDs, is a common expression of the jargon of traditional finance. It exists on the New York Stock Exchange. I think for years it was at a level of 8%, if you can believe it. And now it's down to 4% the last time I checked. FTDs are very common. Here it's an FTD, but it's an algorithmic FTD and it's in zero time, right? It's if you fail to deliver, you fail instantly. So it's real-time FTD, if you wish. So how frequently you're going to FTD is all a matter of, comparing the opportunity and the average return you're making, and it totally hinges on what exactly you're doing. For liquidity forwarding, if you're curious, we've run a bunch of simulations. They are maths, right? So they're not the real world. But it's surprisingly easy to not lose money and to actually forward a substantial amount of liquidity in this fashion, while at the same time keeping a very low level of pass or FTDs or reneges, as we call them. So that's so to summarize, Your question is fundamental. If you don't want to fail, you don't have to, right? We have plenty of strategies that cannot fail, and they won't. So in a way, it's the provision you're putting aside to compensate is kind of useless in this case. But that's we can return to that, but that's the price to pay for having a design space which is super broad. So if we don't attempt to understand what you're doing, then, worst thing comes to worst, we take your provision. So you can play those kind of very conservative strategies that will never fail in principle, and then you don't have a problem. But if you start, and we think it's very economically efficient to risk failing sometimes, then you have to compute for yourself how often this is going to cost you and whether this is advantageous to you overall on average. And sometimes it is, definitely.
So if from the perspective of the initial order, right, if one of the counterparties that gets matched on the order book fails to deliver, right, then the order book should also just match the next possible liquidity in the book, right?
Totally.
So,
It's
at some level,
Sorry. Yeah, you're right. It's completely smooth. So without skipping a step, the market engine will go to the next best offer and so on and so on. And the offer that's failed is going to disappear from the book unless it reposts itself, because so that's an important detail which we may discuss later on. But offers are called twice, actually. Once to execute and once to repost themselves or republish their liquidity. This is how we implement AMMs.
Yeah, correct. And in theory, then, sort of the most kind of non-failing strategy should sort of approximate something like what already exists, right, in a traditional AMMs, which is basically a non-failing liquidity strategy should perform essentially equally to a traditional AMM style DEX, right?
That's
Whereas a failing strategy gives you additional potential efficiency.
That's correct. Yeah, it's a good way to put it. I hadn't thought about it, but yes. So technically, we can reproduce a large class of AMMs, all the ones that are based on what we call cash ratio, essentially some kind of recipe that says for a given price how much of which asset in value, what's the percentage of the, let's say, the base asset you want to hold. And so all the ones you can mention, Uniswap V2, V3, Balancer, something I call Balancer V3, which is a concentrated form of Balancer. But really, it's a very large class, much broader than just those specific AMMs. We can reproduce. There's one distinction down, which is really important, which is that we do not implement the continuous version of these AMMs, but the discretized version, which means that we have to, right, because we're running them as a contract that manages offers on both sides of a book. And whenever we consume on one side, we replenish the liquidity on the other side. So roughly, this is all in the class of we buy low, we sell high kind of mechanisms. And when you do this, you have to do it at a specific price, right? Whereas ordinary AMMs in DeFi operate continuously across price space. So here you use a price grid rather than a price range, if you wish. And the grid, the step of the grid, how distant are two successive price points, that's a proxy for measuring the volatility of the market. So our basic AMM, which we call Candle, is in ways like Uniswap V3, but in ways it also has an additional strategic dimension. So if you remember, Uniswap V2 was extremely simple to use as a liquidity provider, really a breakthrough in terms of anyone can provide liquidity now. any address in the world.
Yep.
And then version 3 came and introduced some more flexibility in how you could drive this provision of liquidity. You could now choose the mean price and the max price. And with a discretized AMM, now you can also manipulate a proxy for volatility, which is, an improvement. And for sophisticated providers, it's a necessary improvement. So you kind of keep the best of both worlds. You are both in front of something which is really easy to use and monitor and reset if you want, with next to zero infrastructure. I mean, just a computer and no bots. Everything is happening on chain, just like AMMs are simple to use. But at the same time, you have this differentiator, which is that you can express some of your beliefs about what will be the current volatility. And that's actually integral part of defining a proper market making strategy, we believe.
It's very interesting because, when you really reason about capital efficiency, like this is a very logical construct, right? Which is that in a sense, what you're doing is you're really thinking about a willingness to fail, right, on a specific fulfillment, right? But the issue becomes that if you actually have, since like effectively an order is effectively a commodity at some level, right? It means that that it isn't a systemic failure, right? It's just a failure of a specific party, right? And then you just move on to the next, right? So at some level, the thing that's interesting is that there's sort of a feeling of if you're not willing to fail, then you're not trying hard enough, right? So in a sense, like that's where the source of the efficiency comes from, right? Is it comes from this kind of like the existence of the failure to deliver, right? So in a sense, like this is sort of the edge of the system, right? So it sounds to me like the risk management in the system is then connected to measures of volatility. So how do you sort of measure volatility?
So by not here. So okay. So I like to say two things. First of all, what you just said, absolutely right. And it's slightly reminiscent of statistical arbitrage, right? So there is not all strategies have to risk failing, but it's an interesting dimension to explore. Having a certain low percentage of failure, probably if you fail too frequently, it's going to cost you and it's unprofitable. Which is good because we want the order book to be mostly clean of failing offers. We want them to be sniped quickly. And we have a specific mechanism for this. We can talk about it later. But what we see in our back testings and simulations is that specific strategies that dare to fail a bit can be both profitable and achieve higher capital efficiency. And that has a kind of some kind of kinship with statistical arbitrage. Oftentimes, we can, for example, this kind of liquidity forwarding process I was describing is a bit like a passive form of statistical arbitrage, which you find in more active forms on traditional markets or on actually centralized crypto markets. And this is often the case. So in a way, we project on-chain strategies that are latency arbitrage, the latency arbitrage crowd already uses in or latency sensitive arbitrage crowd, as they call themselves now, also known as high frequency traders, use already in other contexts. So yes, totally. Taking a bit of risks, risking a bit of failure to deliver is actually gives you access to another dimension of trading or liquidity providing. And specifically, the intuition is that if you may fail, then it means that you're operating within the noise on different price levels, that's a natural consequence of the fact that trading is asynchronous. So the fact that trading takes time, and even more time on a blockchain, that there's a kind of a time of flight between the decision taken off chain, even with very good data and very powerful computers, and the moment it's actually run on chain, that delay, that latency between decision and execution creates a bit of vibration on all markets. Lots of events can happen in the meantime. And so that is typically the this kind of micro changes in prices. That's typically the advantage you're drawing from, you're extracting from this noise when you're playing with potentially failing strategies. That's the first thing. So to your second question, how do we evaluate volatility, current volatility? How do we project implicit volatility? That in that respect, we provide nothing new. You can just use your ordinary signals. You can read it off price feeds. You can do all what people do normally, and all the things, the sophisticated forecasting techniques that people have that I don't know of, but you can use simpler ones, and that can drive the way you provide liquidity via this the choice of this price grid. We see this in simulations very well. The impact of with synthetic data, we are the master of volatility because we inject it into the price process by fiat, and then we see that for a given level of volatility and a certain range of providing liquidity, how discrete our price grid is will have a substantial impact on the mean returns, for example, on a given duration.
So one thing that I might be misunderstanding is the following, right? Which is that it seems to be a logical conjecture that as you get much more liquidity depth in the book, that the costs of failure at the level of the exchange actually is lower, right? So I'm wondering from an incentive design perspective, like, shouldn't there be a concomitant change in the penalty cost, or I'm just trying to understand the design mindset behind sort of the fixed penalty costs, right? Because obviously it's a fixed and low penalty cost, right? So I'm just trying to compute, because as you get a very, very thick order book, then in some sense it's less impactful if any specific market maker, fails to deliver.
I see totally what you're saying. By the way, this kind of discussion, by changing a few words, we could have the exact same discussion if you were having a podcast with 1inch or Paraswap, because they are facing exactly the same problems.
Yes.
They have, I wouldn't say unreliable, but they have FTDs coming from their own private market makers. They have collisions of liquidities. So this is, and they have latency in addition. So this kind of discussion exceeds this simple Mangrovian frame. But to return to your question, so it's an interesting suggestion. So I tell you how we think about it. So first of all, what is this penalty we're paying? There's a formula. And the formula I can decompose into three factors. It's a product of three numbers. First number is how much, the amount of units of gas that the contract that was supposed to deliver consumed before returning and saying, sorry, I'm not doing this. Sure, you don't say anything, you just don't do it. And the market engine will see that you have not delivered in the manner of a flash loan.
Yes.
So that's number one. And you see that since as a provider writing that code, I'm going to have to pay proportional to the number of gas units I'm consuming when I fail, you see that I have an incentive to fail early if I can. So if I know I'm going to fail, I should fail for a low amount of gas. So quickly, so to speak. So that's factor number one. Factor number two, we're going to multiply this by the current gas price according to the platform. That's a global variable, which we inject in all the markets of Mangrove on a regular basis. And the third factor is, and this is where we are connecting to your question specifically, is a kind of a penalty multiplier. So let's say it's 2. What does that mean is that if taker has paid the gas at the price that which the platform says is the price, which is an if, right? Because we can't control that. Then for every $1 that he or she paid for running your contract, your delivering contract, it will be given back too. So it's an incentive for people to actually take offers that fail and be paid for doing this well, which is a reason why the book will be driven back to a clean state. Not a clean slate, but a clean state. So that's how we think about it. Now, who fixes this penalty multiplier? The idea was that you want to keep it quite low at the beginning, so bigger than 1, obviously, because you want to overcompensate. So maybe 1.1 something, and drive it up with some kind of low frequency control if you see that the book is actually hard to keep clean or to keep tidy of failing offers. And in a way, it's exactly what the New York Stock Exchange did. I think in the early 2010s, I think, they had 8% FTDs on their market. And so they brought up the fines for not delivering, and they reduced the
Nice.
FTDs to 4%. So we have a kind of a New York Stock Exchange approach to the problem. Now, what you said, which is, I think, very perspicuous, is that indeed, if the book is very liquid and all the offers are packed on top of another, and whenever an offer fails, it's essentially indistinguishable from the point of view of the taker, then with that kind of book, we could actually maybe bring down the penalty a bit. So, but it would be...
So I have another.
Sorry.
Yeah, go ahead.
I was just going to say,
I,
we have not yet thought of some kind of closed loop formula that would do this. And I think it would be more some kind of control that some kind of parameter it is a parameter that's chosen from the outside. And the problem is, if we can spend another minute on this, is that it's all good to say we will control for it, and we will. It's like a slider, and if we see that the book is not tidy enough, we'll bring it up. If we see that liquidity is high, like you're suggesting, and that everything is fine, then we'll bring it down, because this releases a bit of the friction introduced by this coefficient. If we do this, then we run the danger of AVE, which is to have, absurdly many parameter changes to vote on from the DAO perspective. I don't know how many they vote, but maybe five times a week, down so many places. They have so many parameters to change all the time. So if you have a huge amount of sliders, and and also those penalty multipliers are local to every market. So it's a lot of sliders to manage via a DAO, which is arguably a slow decision process. So we have to be careful with this line of thinking.
Yeah, agree. And I think also, in addition to being slow, there's also the potential for governance level economic attack vectors. So, people could potentially amass voting rights in a manner that kind of favors their style of strategy. So, I do think that becomes sort of a more complex and less linear game theory. One thing I was curious about. So I don't quite understand the mechanism of sort of failure. So is it that the person placing the order is compensated for failure directly, and do they get kind of made whole, or do they actually get a additional bonus? Like where does the penalty fee go?
You get a bonus. So if suppose so there are two cases. Either you're just a a naive liquidity consumer, you have no idea that some of the offers may fail. Doesn't It's not your problem, or maybe but that's not what you're looking for. And so you're just going to shoot a market order. The engine will execute in the best it can. So it will go to the top of the book, trigger the execution of the top of the book's offer. Then, if it fails, go to the next best one, blah, 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 until your market order is filled, as usual. Now, for each of the offers that you triggered to fail on your way to filling the order, there will be, let's say, a 2-to-1 compensation, assuming you paid the gas price, which is the platform's gas price, which means you will be more than compensated for the gas you paid for to no avail, right? Because the offers you triggered, which you funded gas-wise, is actually has not delivered. So that's the way it works. Now, if you're a keeper, so a specialized actor, and we have a kind of a proxy contract for that, who actually is not looking for consuming anything, but actually is just looking for collecting the bounty, which is attached to triggering an offer that fails. Then you'll be looking at the book, making yourself an ID maybe by dry running a huge market order that offers so and so are likely to fail. Go to the proxy contract, snipe them for failure, and then you enter a little piece of logic that's triggering the execution of the offers you suspect are going to fail, pay you the compensation if they do fail, or revert the execution if they don't fail, because you don't actually want to buy, right? So to save you the effort of doing all this programming work, we've done it. It's a proxy contract. You can just directly go there and snipe the suspicious offers. If you're more often right than you are wrong, and the bounty multiplier is high enough, you'll be good. You'll be profitable.
Yes. So I would model this as approximately like it's a bit like the idea of a security bug bounty, only it's more economic, right? So effectively, you're rewarding people for finding weaknesses in the market structure in the decentralized market structure. The thing that I'm concerned about with this model, though, is wouldn't it be possible for someone to basically just if you have a fairly low liquidity market, it may like a pair, like you may find that it's beneficial to just hammer that market with large orders in a very repeated fashion in order to just basically I guess in a way there would be an incentive to sort of beat a market to zero, right? Where they would just continuously place large orders that would fail until the person will withdraw entirely.
It would cost you down. And if we see that kind of behavior, which we'll monitor, because it's easy to extract a failure rate for a given market, then we push the slider up, and it becomes costlier for the person who intentionally fails to deliver to do so. So, and we can and everyone and the money that the attacker or the griefer loses is going to the keepers. And needless to say, Mangrove has written its own keeper bot, talking to its own keeping contract. So we'll be funneling that kind of money back into the system quite efficiently.
Yeah, interesting. This is terrific. Would love to just get a quick thought on, the origins. Like how did this arise? Like how did this get started?
Super simple. We I was I was teaching market making to students in my university, and I was fascinated by the fact that actual market makers don't really have the capital that they play with. They borrow it from the market, they do all sorts of things, they constantly sell something they don't have, and it's only at the end of the day that they close their positions. And so there's this kind of I wouldn't say it's just elegant. I think it's there's this crucial piece of equipment in traditional finance, which is that liquidity provision, which is absolutely central, at least in the kind of market mechanism that we have currently, the dominant one, the order book also the discrete batch auctions. It is a complete necessity that or a factor of efficiency that they don't actually play with the capital of their own. So I was thinking, all right, so why don't we do this on chain? I mean, it would be it would be a tremendous boost to liquidity provision on chain. And as soon as I had the question in mind, I discovered that it's actually quite easy to do. The way you do it is you publish a special contract whereby a consumer will actually send its cash for execution of an order, and the contract will take that cash, deposit it on a lender. You need a lender. Increase its own borrowing capacity, borrow on the back of the collateral, which is the cash of the taker, and send that to the market maker, and the market maker modulo a complement, because you can't really do 100% in value with the current lending systems we have on chain. It's more like 80%, 70%. Modulo a complement, the maker or the initial liquidity provider would actually complete its part of the deal and sell whatever asset the taker was selling. So in other words, maybe a simpler words, but less detailed, you just have to write a little trustless piece of code that's going to intermediate between taker and maker and manipulate the cash of the taker so that the capital of the maker is actually partly 80% borrowed, and so in a way completely virtual, which is quite reminiscent of perpetual markets, by the way. We can return to that later if you wish. And so now we started discussing with Jean and Adrien, my co-founders, and Julien was an economist. We were working, Julien Prat, we were working on blockchain-related research at the time. And we discussed whether this would be an interesting contract to write. And then Adrien said, but to do this, there is no need. We have to write some kind of this third-party contract, which looks like a market. So we need to write down a market mechanism. And then Adrien said, why should it do only this? This is cool. This is some kind of self-leverage. So zero capital market making, if you want to put it this way. But there's so many more things that the contract could do. Why don't we let the liquidity provider give like a tiny little cartridge with it, which is the management code for the offer, take whatever cartridge it wants to take and put it in the slot of our market engine, was the idea. And so here we go. We decided that we can write that very generic contract with a maximally large design space. And the only thing we needed at that stage was to invent this mechanism to make the offers credible. And that's what we discussed before, the penalty system. And that's it. And we decided to do it. At the time, it was September 2020. We quickly had enough code to go and try to fundraise for the seed round, and we got the seed round ready in April 2021. That was a time everyone was super hot on DeFi. It was people are not really thinking twice about investing. It was a very uplifting time. It was a crazy creative energy around us. It was a really, really fun time.
Yeah, that's quite amazing. So I guess, in kind of rounding out the conversation, I'm really curious about sort of what the roadmap looks like. So what are the things that lie ahead and, what needs to yet be completed?
Yeah, so I'll tell you in a sec, but before we conclude, I'd like to just insert a little remark here. We've discussed discrete AMMs, and we've discussed liquidity forwarding, and we've discussed the general design space. So it has to be clear that we have not explored that design space completely. And so the vision of the Mangrove project is to be a platform, a new market mechanism, and we're building on it because we have to, right? Because who else is going to build first? But we'd like to bring more builders on our platform. And why would we like to do this? Because we think that collectively there'll be a far stronger exploration mechanism to exploit all the nooks and crannies of the design space we have opened up. And so I'll give you just one example without unfolding the details. One thing you can do with a Mangrove type of reactive engine, we call them sometimes, is you can do directional trading entirely on-chain. To do this, so directional trading, by which I mean following the price, selling when it goes down, buying when it goes up, which is kind of the dual of market making, right? Where you buy when it goes down and you sell when it goes up, which is perfect for providing liquidity on an order book. Now, if you want to do directional trading or pro-cyclical trading, as people say also, you cannot really do it with an order book because you can't say sell under the price, under the current price. You have to somehow wait for the price to be low enough to sell. So else you will be taken instantly, and that's not what you mean. So stop losses are typical pro-cyclical patterns of trading that you can't really use an order book for. You need a market order, or you need to ask a centralized exchange to do it for you when the price process down crosses a given threshold that you define. So we can actually implement this pro-cyclical trading or directional trading on Mangrove, and the idea is very cute. You want to detect when, let's say, a stop loss. You want to so you have one ETH, you'd like to sell it when ETH down crosses 1500, let's say, but now it's at 1700. So you're way above the price at which you want to get rid of your ETH. What you do? Well, you can't really place a sell order, but you can place a buy order. No one would be interested in it. So you place a bid in the book at 1500 for a tiny amount of ETH. And then you attach a code, which will do a bunch of things, verifying that the price is correct. But if it's happy with the price when it's taken, it will actually post on the other side of the book or execute on a nearby DEX or whatever method you want to use to sell. So to sell at a low price, you're actually going to place a bid at a low price. And by the magic of attaching code to your offer, it will have the same result. So what's the deal here? Well, you can encode arbitrarily complex directional trading strategies with zero infrastructure, zero bot. You can go fishing, and the entire thing is encoded in this contravariant fashion on the book, and it will just unfold following the price action. So this is just to say there are plenty more ways in which people can actually exploit the design space that we have set up.
Yeah, that's really wonderful. I think the interface is truly a tremendous, potentially very naive strategy that would be extremely popular within retail, right? Because in this case, you really just park and then you outperform, right? So in a sense, like, you're really bringing the rewards of marketizing the risk of failure to deliver, back to users in a very simplistic interface. So I think that's a super exciting sort of way to uh, go to market.
Thank you.
That's terrific. Well, I think this is definitely an incredibly deep topic, and your research is quite fascinating. I love the platform vision. I'm very excited to see, new applications that sort of form on top of this very, very open design space as you've described. So, I think it's a tremendously exciting platform and, really, really looking forward to these upcoming milestones. So just wanted to thank you for joining the show.
Thank you very much for having me. It was a pleasure.